Hello everyone, are you able to hear me? Great, great. So yesterday we were talking about how to compute the frequencies of unique words. Basically, doing the word count on a huge text. So one of the approaches, there were three more approaches yesterday, and let me just uh, have a look at it. So these were the few approaches which we discussed yesterday. All right. So Pankaj, we will take your question. There is a question from Pankaj regarding MapReduce. Don't worry about it right now. All right. Don't worry. So we will just slowly go towards that instead of just jumping into it. All right. Let me also share. All right. Coming back to what I was talking about. So, yesterday we were talking about how to compute the frequency of words using our conventional methods. The first approach was to create a hash table and do the counts using a hash table. And second approach were using the SQL. And there were a few more approaches. We'll talk about them. All right. Now, in this approach, do you see any problems in this approach where we are computing the frequencies? We have created a dictionary and we are trying to count the words. Do you see any problems with this approach? Yes. Thank you. Thank you, Peter. So, anybody else? Yes. Anybody else? Do you see any problems with this approach? Yeah. Other than Peter? Yes, that's correct, Shashi. We need to find the words in a hash table and then increment the count. Finding a word in a hash table is a very quick process. It just quickly locates the word, all right, just like an array does. Like in array, if you have to jump to a particular index, it's pretty quick. Yeah. So what exactly the problems with this? Although the answers will be correct in this approach, the problem would be memory. We will not be able to process the data beyond what can fit in the RAM. All right. Good answer, Peter. And all right. Next is, there were two more approaches which you had talked about. Like there was one was with sort and unique, and other was with grouping. Okay. So so in this approach, so it's a standard work which people do in IT, churning the data. All right, churning the data. Here we are trying to convert the plain text from books into word count. All right. So the approach would be to break the word such that it becomes one word per line, then insert the word into one row in the database, and then once we have one column and one word per row, then we say select word comma count star from the table and group it by the word. Does it make sense? Do you think it will work? Yeah. Do you think this will work? Xiao says that when handling things like text, I would suggest using awk and said will be better performance. Yes, we'll talk about it. All right. So this is second approach. My third approach is this. All right. Those who are aware of Unix, could you raise your hand? There's an option of raising the hand. So Xiao is aware of Unix. Who else? Anand is. All right, Peter is also okay. So only 3 4 people are aware. Do you mind if I take a quick? Should I take a quick recap of how does this Unix pipeline works? Will that be all right? Shah, Peter, and Anand. All right. Okay. So I'll just go through the Unix pipeline quickly. All right. And why do I want to do this? Because it will be used in future sessions also. Be it pig streaming or be it Hadoop streaming, in both the cases we will be using this. It's sort of foundational. All right. Is everyone with me? So let me just go through a very simple use cases, and parallelly let's log in into the All right. All right. So here we are. Let me increase the font. All right. So this is our command prompt. Here, when we type a command like ls, it gives some output. Okay. And ls can take some argument as input as well. Like we say ls minus l. Okay. So those are the arguments provided to ls from the command line. So this is the way to execute any command. It gives the output to us. But sometimes a program takes the input as well. A program takes the input as well. For example, if we have to write, and also a program can write to a file saying this is ls.txt. So we are writing the output of ls to ls.txt. So ls, instead of giving us the output, it gave that to ls.txt. If you have a look at what is inside ls.txt, you will find that whatever it gave us on the screen, it has saved it to the disk. Okay, have we started the recording? Yes. So instead of putting it on the screen, it has put it in the disk. Alright, so any program can give its output to the file as well. And every program can take the input from the user and put it into on the output. For example, let's take a case of read. Okay, read x. So read is reading a variable here. Now when I say echo $x, it's giving the input output to us on the here itself. Okay, similarly, if I use a cat command right now, I can see what is there inside a file. Okay, now what I can do is I can also I can take the input from the screen and print it back, and save it, let's say, to c.txt. Okay, so now I am giving the input cat is reading from stdin and saving it onto c.txt. Okay, cat command, I'm saying write it to c.txt. Also please note that this time I'm using double arrow, which means appending rather than overwriting. Single arrow is for overwriting. So what exactly is happening here? Cat is taking input from you from stdin and saving it, giving it to the std out. Okay, cat is giving it to the standard output. So cat is taking input from standard input, putting it onto standard output, and right now we have marked our output to go into c.txt. All right, now let's have a look at what is there in c.txt. So cat is having two options. One, when you provide an arguments to cat. Okay, when you provide arguments to cat, it just prints whatever is there in that argument. So, and in case you don't provide any input any argument to cat, just like this one, it takes the input from the standard input, which is this where you type, and puts it into the standard output. Sounds good? Now, so this was about general programs. How can, so the program takes input from standard input, give the output to standard output, and sometime to another stream called standard error. Okay, all right. Now there are a few important things here. Sometimes you want to pipe the output of a file to some other program. Since the way cat was reading from standard input, any program that can read from standard input can receive the input from other program. Okay, instead of cat taking the input from us, it will take the input from another program. All right. So similarly, if we have, let's say, WC. Okay, WC is a word count program. Whatever you type here, it will do the word count in this. Okay, and then will tell you how many total words are there. Okay, it just counts the number of characters, not unique characters, just the characters, and total number of lines. This is total number of lines, total number of words, and total number of characters. All right, so WC took the input from us when we typed. Now WC can also take input from another program. Okay, because WC can take input from standard input. If we change the standard input to say this, now WC, instead of waiting for you to write, it will take the input given by cat. Alright. In other words, cat is giving out the data to standard output and WC is reading it. Alright. Now you can see that it has done the word count and character count on the input provided by cat to it. Okay. Similarly, there is no limit to what we can do. So you can see that we have again done the count of this count. So this total number of counts are actually 26. These are spaces here, then these characters, and then this. Okay. Therefore, 24 characters, 3 words, 1, 2, 3, and 1 line. Alright. So word count has done the word count of another word count. Alright. Now there are so any program which can take the input from the standard input can be and gives the output to the standard output can be used as a filter. Alright. Now there are few more things we should know. There are few more commands we should know. So we talked about and also you remember the ls command. If you just want to find out how many lines are there, we can simply say ls pipe wc. Okay. So it has counted the number of lines, number of words, and number of characters in ls. So we have got 22 files. So similarly, you can see here. All right. So Murkesh is not able to hear. Are you able to hear? All right. Everybody else can hear, so I'm assuming that there's something wrong with Murkesh's audio. So let me just send him a message. All right. So good. Now there was a question, what is the character at the end of input? At the end of input, we can just press Control D and that will be end of input. All right. All right. Similarly, we can do these, we can pipeline all of these Unix commands one after another to solve our problem. All right. Now let's say, let's create All right. Now let's try to do something here. And going back. Where is the... All right. So we talked about how we can chain the commands together to get the results. All right. So let's try to do the word count and let's try to understand more commands being used in this scenario. All right. So there are many commands in Unix which we all would like to know. One of them is SED. SED is a stream editor. SED is a stream editor. It does a lot more work. Okay. So what does SED do? SED basically replaces. So I'm just taking one use case. There are many use cases and would be very difficult to explain even in couple of hours. All right. So SED replaces a word with another in this scenario. And the way we define it is S, and here is the word, okay, to replace, and then slash with whatever. Okay, so this is how we the syntax of SED is. So let's see if it works. So if we say echo hi, how are you? Okay, so echo just give whatever you argument you give, it shows on the screen. Let's try to replace hi with capital Hi and comma. So now it is replaced in this stream itself. Whatever input it got from echo, it has replaced hi with hi, and this is what it is. Okay. Now in this input, now in this file, see that we can replace far more. If we had multiple lines, even in those we could replace anything. Then there is a command called sort. It orders the data in input. Okay. So sort will take whatever input is given to it and will order it. For example, and let's say here, let's try to replace space with a new line and then see what happens. Do you see that? It has replaced space with the new line. Now we can do things like WC, or we can do things like sort. What does sort do? Sort basically orders the data, so alphabetically. So A, H, H, Y, Y. All right. All right. Now in this case, you can see that we are sorting the data. So how has come along? So one more thing I want to do is, all right. Now you can see that how has come along. I mean, both hows have come together because we have sorted the data. Now there is another command called unique. What does unique do? Unique basically finds the unique words. You can see that it has found the unique words. It has removed the duplicate how. Okay, you can see that it has removed the duplicate how. It has unique has got one argument called minus c, which displays the counts of unique words as well, other than only finding the unique words. So this is how, using these Unix commands, we were able to compute the unique words count. Any questions at this point? Is we are basically saying count the distinct words. Sounds good to everyone? Is it clear? All the commands, echo, sed, sort. So how many commands we have in this one? How many commands are there in this line? Yes. Can you name those commands, please? Those who are saying other than four, what are the those five commands, please? In this, yeah. No. So minus C is not a command. It is just an option which we are providing to unique. All right. Minus C is not a command. All right. It's only echo, SED, sort, and unique. These are the only commands which are there here. All right. Yes. So Carlos suggests that why can't we use awk? Definitely we can use awk. Instead of SED, we can use awk. And even if we are trying to do what we did, please note that so in awk also, awk is a proper programming environment. There is a command called awk. Let's say uh, so you can the similar to SED, we can also have awk. Awk is also really powerful command line tool, which can do probably anything a full-fledged programming language can do. Okay, but again, if we try to create a hash table using an awk and try to put a word, again, the problem will remain the same. The memory overflow will occur here also. Alright, now there are few more things I forgot to tell you about this command called sort. Sort minus s 1g. What it does is, it does the sorting of the input even if the data is hundreds of gigabyte without consuming that many hundreds of gigabyte of RAM. It will only consume 1 gigabyte of RAM. Okay, minus capital S 1G means it will only consume 1 gigabyte of RAM. Alright. So Carlos, would you suggest some awk way of doing it? I'll like to have a look at it. That will be great. Yeah. Or you just intend to learn awk? Yes, Kamal, you have raised your hand. Yes, Dirpu. Yes, because awk is a very powerful tool. You can do a lot of things with awk. I mean, almost everything could be done with awk, just like we can do it with any programming language. All right. We can replace SED with awk, and we can also code the first example with awk. But I'll not get into the details right now. All right. So here, what we have been able to successfully demonstrate how can we use this chain of command, or this pipeline, to do the word count. Okay, is everybody convinced? Sort minus s 1g is, I'm trying to answer to Shashi. And Rohit, I have not told the problem with SQL yet. No worries. So it's not that you did not hear. Now, okay. So all right. Now here, sort minus s 1g orders the input, keeping maximum memory consumption to 1 gigabyte. All right. Is that clear, Shashi? Great. So these are the arguments. If you want to know more about any of these commands, you can go to the terminal, and let me just take out my terminal so that, all right. So you can say man sort and it'll give you the manual. All right. Now, great. So both the approaches, we talked about SQL and we talked about Unix. Now, do you see any problem with SQL approach and this approach? Yes. Now there is a question from Harita. When sorting with 1 gigabyte of RAM, where will it store intermediate result in the disk? Alright. So all it will do is it will sort the data 1 gigabyte at time, and then after sorting it, it will merge all of the data and give you the results. Alright. Now next is, so Srini says Unix approach is much better than handling at much better handling RAM. Peter says that it would be faster if it utilized multiple computers cores. Correct. That is good. Let me just make a note of this one. All right. And Pankaj says that do you not think SQL approach is slower in terms of performance? Okay, and why do you think so? I do think that yes, SQL approach is slower, but why do you think so? SQL group by will have performance issues with, okay, Okay, so that is Anand's point. So Carlos's point is maybe the next example would see cell scripts also. Yes, in we will when we talk about Hadoop streaming, we will use cell scripting. All right. Pankaj says that round trip and sorting using group by. Okay, okay. All right. All right. Good. So, any other suggestions? What are the problems do you see with approach number two, which was SQL, and approach number three, which was Unix? Okay. So, there are problems with both of these approaches, and those cannot be handled. All right. So, the moment the data starts going beyond RAM, the time taken will keep on increasing. Okay, and as the data keeps on growing bigger and bigger, there'll be many things which will become the bottleneck. First will be your CPU. Also, for Peter, who was asking that we could make it parallel, there is a command. uh, okay, yeah, it'll be faster using multiple cores. Okay, if if you talk about cores, we can utilize that using a command called parallel, which utilizes which runs processes in parallel and makes sure that it basically utilizes the CPUs. All right. Now, as the data keeps growing bigger and bigger, when more data need to be sorted, the CPU will start becoming the bottleneck, as well as disk speed and disk space. Here we have overcome the limitation imposed by RAM. So RAM will no longer be the bottleneck, but as a consequence, the CPU and the disk speed and disk space, both will become the bottleneck. And as a matter of fact, when you run this program on hard disk drive, the time taken, so when you run all of these things in parallel, the time taken by reading the data from the disk is actually greater than the time taken to sort the same data. So if one process is sorting the data and other process is reading the data into the memory, the time taken will be mainly into reading from the disk. Okay, so these three things will become the bottleneck. Now, what do you suggest? What do you suggest? So Peter was suggesting something here interesting. He was saying using multiple computers or multiple cores. Anybody else? So now let's have a look at one of my plans. So let's say we come up with this something called external sort. We decided we thought about it that our disk is becoming bottleneck and our single computer is becoming bottleneck, and we thought that let's do the sorting using external machines. So what we did was we we got two more machines. So now we have three machines. One we call launcher, other we call machine 1 and machine 2. Okay, from the launcher, or maybe launcher is on any of these machines. So from the launcher we sent half of our data to machine 1 and half of our data to machine 2, and let machine 1 and machine 2 do whatever our earlier approaches were, whatever approaches which we have discussed so far. Okay, using those approaches we computed the frequency of words individually on machine 1 and machine 2, and whatever results we get, we merge it. Okay, we merge it. Okay, merging the sorted input, will it be easier or harder? Does it involve a lot of work? All right, so while merging the result written by machine 1 and machine 2, okay, will that merging be very inefficient, or can it be made faster? All right, so we talked about approach number one, which has the bottleneck of memory, which is the hardest bottleneck you will ever face in computing. Then we talked about SQL and Unix, in which memory limitations we had removed. We only had the limitation of the disk and CPU. So what we are trying to do is, now we are trying to utilize multiple computers to solve our problem. So on the from the launcher we are launching work on machine 1 and machine 2. Half of the text we are sending to machine 1 and half of the text we are sending it to machine 2. All right, now both machine 1 and machine 2 will order the data and count the word frequencies, count the distinct word frequencies, and whatever result we get, we compute the distinct of both of the two. Now, when we are getting the output from machine 1 and machine 2, do you think we'll have to again sort? No, we don't have to sort it again. Alright, we don't have to sort it again. Why? Because this data which is coming from machine 1 and machine 2 is already in ordered form. You can see Ray has come before Sa and Ga has come before Ray. So it's very important to note that we let machine 1 and machine 2 both independently order the data, do the word count, and give us in the ordered manner. Instead of in giving it just the frequencies, no order, but we want both of these machines to give us in the order. Now merging these two, do you think it will be too big a task? Will it be easier or harder than sorting? Will it be faster or slower than sorting? Merging these two data sets. Correct. Correct, Harita. It will be easier. Have we talked about how will it be easier earlier? All right. Here is a question from Anand, and we'll try to see if we can resolve it. Good. Very good questions. Now he says that if machine 1 returns ADE and machine 2 returns BCF, in this case the sorting will be required or not? No. Alright, I'll show you the approach. We call it merging. When we merge the two texts parallelly, that's called merging. I'll show you how to do the merging. Let's say, imagine yourself standing in an assembly ground. There are two queues in front of you. You are facing and you are the person who is addressing the queues. And in these queues there are people standing in their increasing height. So the one who is closest to you, as in you are facing all the people, okay, facing all the queues, and the person who is closest to you is the shortest in the queue, and the person who is away from you is tallest. Now you are standing in front of the two queues. All you have to do is pick up the sorter who is in front of the queue and put him in another queue, and keep on doing it again and again, and that will merge the two queues easily. Similarly, when we get the two results which are ordered from machine 1 and machine 2, we can merge in the same manner. So let's say 1, 2, 3, 4, 4, 11, 10, and say 23. Now another one we have is, alright, let's say these are the two results which are in ordered format. It's greater than, from machine 1 this is what we got, and from machine 2 this is what we got. Alright, if we have to merge these two, it will be quite straightforward. We'll just compare who is in front of the line. So these, okay, out of this we'll just take one, put it in another queue. Alright, although we don't have to put it in another queue, we can actually merge it in line. Okay, but that's something which we can discuss later. Again, we will compare these two. Do you see that? We will move both of them in case both of them are equal. Alright, then we take another two and compare these ones again. So out of this we take out 4 3. We are basically taking the smaller one out of these, and putting it in another queue, fresh queue. Out of this you can see that I'll just pick up 8, then 9, then 10. All I'm doing is going to the front of the queue, picking up the smallest ones and putting those in a new queue. So we have been easily able to merge. Now there are a few things you need to know. First, we did not have to read the whole data to merge. We just have to read one member from both the queues and we were able to merge happily. Second, we did not have to go through this data more than once. We just had to go through this data once. Okay? So is everybody convinced? So Anand, is it clear now? Alright, so this is how merging happens. This is a very important part. Okay, that's why I've taken this full example of merging. So merging the sorted data is far more easier than sorting the data. Sorting data requires lot of times we have to visit all the elements. And the more number of times we visit the elements, the complex it gets. Complex when we say, it means that how much time will it take? The time complexity will keep on increasing. Alright? So this is how we can sort. Now we talked about this example, this external sort example. Do you see any problems with external sort? Anybody? Dirpu, Peter, Xiao, Dilsad, Haritha, Carlos, Sashi, Rohit, Srinivasan, Srini, Pankaj, Murugesh, Kamal, Anand. Do you see any problems with external sort? Yeah? Alright. Peter is saying if you have tons of cores and computers, it will start getting costly. That's okay. Yes. Sydney says it is definitely more efficient than the previous two. All right, what exactly is the problem with this sort? All right. So as a matter of fact, the architecture of Apache Spark is partially like this, okay, whatever we have just discussed, but there are problems with this approach. Okay, the problems is first problem is the time consumed would be there in transport of the data, because you are sending the data to these machines, and these machines are doing the work and then sending it back. So if we are on Hadoop, this at least this work of sending the data will be reduced, because the data will be already in the form of data blocks and will be available already on all the computers. So at least one side traffic will be saved. Second is, for each requirements we would need to design special purpose network oriented program. If you see here, every time we do something, we'll have to design our own special purpose program, right? Second is, it would require a lot of engineering, because imagine this: when you are sending work to launcher 1 shuts down, or while launcher work was working, it there was some problem with launcher 1. Now we have to give the same work to somebody else. Now that somebody else might also shut down after some time. Now, to how do you, I mean, you'll have to keep monitoring all these machines, reassigning the work, and keep on working on it. So this will basically make it really slow. Okay, really slow, and it'll require a lot of engineering from our side. So is everyone with me? Was I able to establish that using MapReduce might solve the problem? Okay, all right. So, so what exactly is a MapReduce? MapReduce is a programming paradigm. It's a way of solving sorting intensing problems. It is good for solving the problems which involve sorting. All right. Now, in case of MapReduce is a kind of a framework which runs on top of Yarn to do our to the do the to do the to handle the sorting intensive jobs. All right. We have to we have to code two kind of function. One is mapper, other is reducer. The mapper converts our input to key value pairs, and reducer aggregates all the values. So if you think about MapReduce is a framework which basically is a big machine, which basically is a framework which sorts the data. The sole objective of MapReduce is to sort the data, order the data, and on what basis? That basis is defined by your map function. That basis on which the ordering of the data happens is defined by your map function. So your map function takes the raw data, converts it into key value, and gives it to Hadoop. Hadoop takes these key values, and then based on the key, it groups all the values together and forms key and array of values. That's what Hadoop does. And once it has formed key and array of values, it feeds this key and values combination to your reduce function. all right, so that the way you run an aggregate function in case of SQL, you can also do something on this group of values. You can do many kind of things: computing average, computing count, computing sum, computing concatenating these values by comma, computing the unique of all of these values, and you can do so many things in the reducer. And so effectively, using map, you can clean the data, you can restructure your data, parse the data, and and form a, a, a criteria of and form the criteria on which Hadoop will sort your data. Okay, that criteria, the key can be composite key or it could be a single key. Okay, all right. Now, when you are running a map reduce, the reduce phase is optional. Sometimes you don't want sorting. Whatever is the output given by the map, you want it to be stored directly in the output. Alright? Now, in case of this map reduce as a paradigm has been fairly successful, and therefore MongoDB, CouchDB, and Cassandra kind of databases, along with Apache Spark, they have all adopted a similar map reduce. Okay. Now, mapper and reducer can be written in Java, Shell, Python, or any binary in Hadoop. Okay. Mapper and reducers in Hadoop can be written in Java, Shell, Python, or any binary for that matter. We will show you how to do that. So there's a question from Pankaj. Question is, so mappers function can have duplicate key? Yes. All right. And those all the values for each key will be aggregated together. Now let's have a look at this flow which I prepared. All right. So when mapper is giving output, it can give the same key multiple times. All right. All right. Let's have a look at this. Let's imagine that there is an input line that is fed to the Hadoop, and you are trying to compute the unique. All right. So let's say sa re sa ga. This is this is the content of a line. This is the content of a line, and this is being fed to your map function. This map function is a very simplified way of saying. All right. So here, this particular map function, what exactly it is doing? It's iterating word by word over the input and then printing word comma one, meaning word is the key and one is the value. Alright, so it has converted this input line into this. So that's the role of mapper. Mapper doesn't have to bother about anything. All it has to do is convert an input record into key value. Here an input record is a single line, and key is sa, and value is 1 again. So Key is a string and value is integer. So that's all map has done. Map does not do any sorting. Map leaves the sorting to Hadoop because, as we have discussed so far, sorting is a very intensive process, and MapReduce is nothing but a sorting framework. Now it runs these Hadoop runs on this key value and orders it and then groups it. So it is grouped like this. It's, you can see Ga has come before Ray has come before Sa, and these are all the values are grouped together as a big array. You can think of it. Now, once Hadoop has done its job, this dashed line represents Hadoop. Once Hadoop has done its job, I mean, map reduces sorting has finished. After sorting has finished, Hadoop is going to call your reduce function. Okay, these are two functions coded by you. All right, these are the two functions which are coded by you, and okay, now this reduce will run on key and array. So ga will go as a word in while executing reduce function, and this array will go as the second argument. So the reduce function can do anything it wants. Okay, for example, here it's saying array.sum and passing this frequency array is basically summing up the values of an array. So the output of reduce is ga1 ray1 sa2. Okay, is this clear? Is this diagram clear to everyone? So in this case, the value is map is forcing the value as 1. We could also say value like this, or we could say something else, maybe another word. So whatever we want to put as value, we could have put that value. All right. Whatever we require as part of our output, we will put that as value. It will go in the output. All right. That makes sense, really. All right. Now, this was just how it runs on single machine. But it will also run well if there are multiple machines. Imagine there are two nodes, each node containing a file of input text. Okay, so these are maybe two parts of the same file, one block in one node, another block in another node, or you can, as we already know that in HDFS, when we store some data, it's broken down into blocks, and those blocks can be processed parallelly on multiple machines. Okay, so let's say there are node 1 and node 2 containing two parts of the file. Half of the part is in node 1, half of the part is in node 2, and node 1 is also running the same function what we had discussed just now. The same function is sent to both the nodes, node 1 and node 2. Okay, data is not transferred. It is this function which is traveling. It is this code which is traveling. Okay, so mapper is our mapper code which converts the input record into key values has been run, and you can see what's going on in the right hand side. You can see that in stage number 1, on the left hand side the values were sa re saga, on the right hand side the values were sa re sa, and after the map has finished on both the legs, here and here, you get this and this. Okay, and this happening in parallel on both the nodes, and once sorting has finished on both the nodes, you get something of this sort. Alright, now since one key which is on the left hand side could also be there on the right hand side, therefore the results from both the sides need to be merged. Okay, because all the values for a key need to be brought together. All the values of a key need to be brought together, and therefore this. So this and this are merged together to give us this. So Ga has become one, Re has become this, and Sa has become this. Alright? And after that, after merging, we can run the reduce, and it will basically and our reduce was doing nothing much but just computing the sum of all the values, and therefore we'll get this result. Alright? Are you with me? So this is another visualization of MapReduce. On each machine, let's say there are three machines, machine 1, machine 2, machine 3, or there are three data nodes, data node 1, 2, 3. On the data node 1, we run the map against the split. Please note that split is similar to the block. It's just that more logical, as in we convert the block, we read the blocks and load it in split. So as part of map, we load the input, prepare the key values, and sorting is happening here. And after we have sorted the data is carried to another machine or maybe one of these machines, and the merge will happen here. After merging has happened, meaning all the values of a key are gathered together, then we will run the reduce on each key value. And then the result is put into the HDFS. Okay, so we start with HDFS. These splits are cut out of HDFS because these are three data nodes containing these blocks, and then map is running on that. Now you can notice that the when the data travels from the split to the map, it doesn't travel over the network because map has been sent to the same node. Where is the data? If there are 500 nodes and your file is only on three nodes on out of these 500 nodes, so your map will run only on those three nodes containing the actual data, because transmitting data is far more costlier than transmitting the code, because our code might be hardly 1 kilobyte, okay, while the data would be minimum 128 MB because of the blocks. Okay, so now you can see that. Now Srini's question is, on which machine does the merge and reduce function run? It all depends on which machines are free at that point of time and are also nearer to these existing machines. Alright, and sometimes we can have merge and shuffle as after merge and shuffle we could have reduce. I think a better diagram is this one. Alright, so sometimes we can have multiple reducers, while number of mappers is governed by how many blocks does your file has. If your file has three splits, mapper will be run on three nodes. If your file has 10 splits, mapper will be run 10 times. Okay, that's something pre-decided by Hadoop. Although you can enforce the number of mappers by yourself, but number of reducers is something you need to think about. When your reducers are overloaded, meaning when your aggregation function is running, if it's taking too much of time, if your aggregation function is really complex, maybe you are trying to compress all the values and put it into single value. So those kind of tasks, if if it's taking too much time, you should generally split it into multiple. And if you split it into multiple, this is what happens internally. So each of these nodes, while preparing the key and value, it will put it in two buckets. If there are two reducers, there will be two buckets created on each of these nodes. Okay, and those buckets will be carried to corresponding reducer. If there are 10 reducers which are running, there will be 10 buckets here, and mapper's output will be kept in 10 different buckets and sorted, and then it will merge somewhere. All right. Now, question from Rohit is, since reducer result is saved in HDFS, does it also get replicated or is it controllable by the user? Yes, it gets replicated. Okay. Can you go over slide number 60 once more? All right. Yes, Shashi. So there are two data nodes, node 1 and node 2. This is our input split on both the things. Here we have input as sa, re, saga. Here it has input. There will be many rows, mind it. There will be many rows like this. It's not the only row. There will be more data. Okay, something of this sort. All right. Now, once map has prepared the key value, those key values are going to get sorted here and then merged, and then the output is going to be passed through the reduce function, and once it has been done, the results are going to be stored in HDFS. All right. There was a question from Peter. Are nested MapReduce common? No. Nested MapReduces are hardly used. I mean, at the end of the day, you will have to convert the problem into normal MapReduce. Okay, good. This is a good question from Harita. Question is, will the final output here is two output files because we have two reducers? Yes, that is correct. There'll be two output files. In slide number 63, will there be duplication in part of part 0? So if a key has gone to part 1, it will not go to part 2. Okay, if a key has gone to part 0, it will not go to part 1. So there will be no duplication. All right, it's a guarantee that Hadoop provides you, that one key will always be passed through one reducer. All the values of that key will be passed through that reducer. It won't happen half of the keys, one key with half of the values have gone to one reducer, and another in another call it will have another values. No, all the values will be together. All right, moving ahead now. When you think about MapReduce, when map is preparing the ground for sorting, and then aggregation is, ag- I mean, the reduce function is combining all the values for a key. Okay, so it looks like a group by. You can always think of MapReduce kind of a group by. Okay, the way you have group by clause, which tells that our data need to be grouped on this basis. Okay, and all the values for that key are going to be brought together by MapReduce. So, all right, now, so that was our quick introduction to MapReduce. Now I would like to leave you with few questions here. So just give me a second. I'm trying to locate the one discussion things I had with. All right. All right. So let me take one more case. Let me take one more case. All right. Let me take one more example for you. All right. Let me take one more example. Then I'll give you a few problems, and that you can solve. Okay. So question is, you have a million files. All right, million music files, and you want to eliminate duplicate ones. Million files, not music files. Okay, duplicate files. What are you going to do? Or you have 10 million files. All right, I'm going to just take a case, and imagine that the each file is less than say 10 MB. Okay, and anybody has some suggestions? Yeah. All right, I'll just take this example quickly. So what is mapper going to do? Mapper is going to prepare the key as a hash combination of and hash and, or let's say just keep the combination as key as hash of the file. Okay, correct. So Anand says that create a similar key value pair and retain only one. So in map, we expect the whole file will be given as input. We will talk about how can we configure Hadoop to send us the whole file instead of one line at a time. Okay. So here we will compute the hash of whole file. Who knows what is a hash? Hash is a signature tool, and there are many such things like MD5 checksum, SHA-1. There are many algorithms which can give you a signature which is difficult to produce by altering the content. Okay. Yes. So the mapper is computing, that's correct, Pankaj. The mapper is computing the hash of the content of the whole file, each of the whole file. All right. And the reducer will be given the key. Okay. And the value will be, let's say, value will be first 10 bytes of the file. Okay, we are assuming that if we first compare the key, okay, compare the hash of the file, and if the hash is same, and then we compare just the first 10 bytes, that should be good enough to establish that a file is same, the files are same or different. If hash as well as first 10 bytes are same, then we can say that the file is good enough. Okay, but collision of a hash is a very rare phenomena. Okay, or what we can do is we can combine, to make it really good, we can say uh, a composite key, as in a hash of the file, hash of the this thing, combined with say combined with colon plus the size of file. Okay, so if we combine hash and size, the chances of collision or become almost zero. Or here we can then give file name. In the reducer, where we will get an array of file name 1, file name 2, and so on. Okay, in the reducer, what you can do is you can just decide which one to delete. Okay, keep file name 1 and delete file name 2. Okay, and so on. All right, sounds good to you? Is the logic clear to you? So hash is a way of computing signature. Now let me show you. Let's say here is a file. Do you see the file? This is a zip file and I want to compute the signature of this one. So I can say MD5 checksum and compute it. So do you see the signature? This is the signature. Okay, no matter what is there inside the file, the signature does a good job of keeping it of the same size. Do you see the signature of the second file? So it's a cryptography. So let's take a bigger one. Now you can see in case of part 00, this is the signature. All right. So in this example, all we did was we made the key as the composite of hash and size of the file, because even if the size is same and hash is same, it's a very rare probability. Okay, it's a very rare probability. All right. So this way we can compute, we can basically deduplicate the files. All right. Now there are a few questions for you, and then we will discuss more details about MapReduce, and then we'll take a break. Or maybe we can take these assignments for later and move to the next session now. All right. All right. One more request I have to all of you. Those who have finished, tried to attempt the quiz earlier, please attempt again because as I was telling you yesterday, that by mistake I had deleted one of the machine, our nobigdata.com, because of which we had a loss of 1 week data because we had the backup of 1 week ago. Okay, the yesterday's backup was gone and the others were also gone, so it was a blunder on my part. While removing the cloud labs, I actually removed nobigdata.com. So that's why you will have to attempt your quiz again if you don't see it in my results. All right, I extremely apologize for this. All right, so before we move forward with more details, let's do some hands-on. Okay, let's do some hands-on on how does the MapReduce job actually look like. Okay, we'll create the most simplest job first, and then we'll keep on going into little more complex. All right, so out of all my experiences, what I found is that learning MapReduce using a using using simple Unix command is far more easier than using Java. For that matter, when I started my career with Hadoop, the whole recommendation engine I wrote using just my Python script. Although I was new to Hadoop, I was new to Python, but I was able to, I still loved writing it in Python or writing it in Hadoop streaming instead of Java code. All right. Now let me describe what does it mean by. All right. Thank you, Shashi. If you attempted the quiz again. All right. And all right. So the Hadoop streaming. So Hadoop MapReduce job can be written in Java. So that's a primary support from Hadoop that you have to write your MapReduce job in Java and then it will execute it. So far we discussed only the pseudocode. Now let's try to do it, get a little, make it a little bit more real. So a Hadoop library, it's a streaming job is a Hadoop library which makes it possible to use any binary as mapper or reducer. In the classic Hadoop, it was only possible to write it in Java. So somebody wrote some MapReduce Java library which does nothing but calls external programs for mapper and reducer. And those external programs you can specify in the arguments. Okay. The only difference is there's a minor format differences. First difference is that mapper gives out the key and value separated by tab. If there is no tab, the whole line will be considered as the key. If there is if there is no value, okay, then I mean if there is no tab, that means it will think that there is no value. Okay, and if there are more tabs, everything after first tab will be considered as a value, single value. All right. So here, when you say key tab value, the this is how you have to give out the output. You have to print to the screen in the form of key tab value. That is first thing to note. Second is reducer will get the data which is ungrouped, which is only sorted. All right, that is a design decision because Hadoop streaming it was supposed to work like Unix pipes, and therefore giving out everything like so in ungrouped manner was easier. So actually, what is exactly streaming job? It's a Java code. Somebody wrote a Java library. Like we will write our Java MapReduce code. Somebody wrote MapReduce code in Java which basically calls external programs rather than applying its own logic. And these external programs can be configured over the command line. Let's have a look at this. It says that, All right. So it says that Hadoop, jar, and then this big a name. In case you are on any other machine and you are not able to locate this, you can use a command, find command, saying find name this, and you can also send the errors to dev null. All right, by saying this. All right, this is secondary. So you can, if you are on a fresh system and you are not able to find out where is this library or where is my Hadoop installation, you can do this. This will tell you where exactly is your library. That makes our life easier. Next is that we can run this command. All right, let's see what happens if we run without any argument. It says that so no arguments given. So this program called Hadoop Dash Streaming is being run, and it is saying that please provide the arguments. All right. Now let's try to run it properly. Now this Hadoop job will take our input directory from here. Okay, and you can see that this is an HDFS file. You can go into Hue and check, or you could say Hadoop Hadoop fs minus ls this. You can see that there is a big .txt file in there. If you want to have a look at it, we can say Hadoop fs minus cat and then say more. More is to see the page wise, to see the output page wise. So you can see that it's a big text file. It's basically all the books of Con Doyle bunched together. All right. So So that is our input, and this input is in HDFS. Okay, you can check in the Hue. And this input is a folder. We can also provide file. If we are providing a folder, it is going to combine all the files in that folder and give your program line by line input. Okay, now this is our output folder. We are going to save our output in this, and this is our mapper command, and this is our reducer command. Here, mapper is doing nothing but printing one word in a line. When it is only one word in a line, that means there is no tab and the whole word is considered as a key and the value is going to be null. Okay, so mapper would be our sed command. What does this sed do? For each line which is being fed to it as input, it's converting that into one word per line. Now that output will go to Hadoop and will be grouped together per word, and then it will be, it will be ungrouped by streaming actually, and reducer will get the data sorted alphabetically. Okay, so here Hadoop is just doing the job of sorting. So it says that the input command not found. All right, now let's just put one more slash here. Why are we putting these slashes at the end of line? Either we can put everything in a single line, or let's say ls minus l. Either we can write it this way. If we want to write it on multiple lines, we can put a backslash and put minus l. You can see that is the same thing. So to break one line into multiple line, this is what we do. All right, it gives us a URL to track the job. We can use this URL to see what's going on. All right, so it's saving our output in this folder. Now please note few more things. One, These input folders and output folders are in HDFS. In input folder, we are starting the name of the file with slash. That means we are providing the absolute location. Here, we are not starting it with slash, which means it's a relative location and relative to the home folder. And that's why it has saved it here. We can see what is there by Hadoop fs minus ls and this folder. Alright, you can see that there is a part and we can say Hadoop fs minus cat and this. You can see it has computed the word count and this is the output from your unique minus c. Alright, what does the more do? Okay, if you have a big file, alright, if you have big file, let's say there's a command called yes. Alright, yes keeps on printing yes on the screen. Okay, and if you want to see the output page wise, you can use yes and coupled with some more things. Now it's not stopping. Wow. Alright, it's better to log in again. To see the things in page wise manner, we can put more. Alright, just a second. I think I've logged out. Right. So here you can see even in this case there is this file, and to see few lines out of a file we can use a command called this, and if you want to see the whole file we can use a command like more, and you see the more at the bottom, it is basically displaying things page wise. Alright, now let's take a break, but before that I'd like to give you this command which we just executed. If the output folder already exists, it will give you an error, so you'll have to change the output folder before executing it. Alright, so we will just take a break back by 8:48 AM IST. Hi, should we start now? Hi, should we start now? All right. So there's a question from Dilsad. Question is, can you explain what is user bin in Reducer? Basically, when you execute a program, you can either provide the full location of that program, or you can just provide the program name. Okay. So if you provide just the program name, it will look into an environment variable called $path. Okay. It'll look into the environment variable called path, and then search in those places. Okay. So when you say any command, whether whatever command you execute, say here, when you execute ls command, it's going to, we did not specify where to find the ls command, so it is going to go in this variable and run will find it in those locations. Okay, these are the locate list of places where to find the executable programs. All right. All right, now, so also please note that it's actually quite easy. We can try executing it without any bin also, and it will run perfectly fine. We can actually change it to this will be perfectly fine, no worries. Okay. Yes, it's a path to unique command. All right, you can see that it's running fine. At least map phase is finished. Let's see if reducer runs fine. It has done the good job. All right, had it not been able to find, it will give us an error. You see that? All right. Yes, we can monitor the job here, right? All right. You can see the job browser via job browser. You can have a look at various jobs. Thank you, Anand, to let me know. All right. So because I was struggling to get the job ID and all. All right. So whenever you run a job, you can go to the job browser and have a look at. Generally, this path, which is displayed by any job, is good enough. All right. Coming back to where we were. So this is what is happening right now. So here, our each line is getting converted into one word per line, and then it's being only ordered by the streaming job, Hadoop streaming job. Basically, Hadoop is first sorting and grouping it, and streaming job is ungrouping it. That is a part of the design of streaming job, and unique command is then being applied on this. All right. Good. All right. Similarly, if there are multiple reducers, this is what is going to happen. Each line is going to be replaced, converted into one word per line, and then parts of these keys will be sent to different reducers. All right. Now, are you happy with this output? Are you happy with this output? Do you want to change something in this? Yeah. So our Hadoop, our job, which was cleaning the data and counting the words, has done this kind of job. Are you happy with this? Peter wants to sort it by most common word. All right. In unique minus C, what is the full form of minus C? That's Srini's question. Minus C means counts. Display the counts of unique words. Find the unique words, but also display the count of each one. All right. So, are you happy with this word count, or do you want to make any changes to it? This is the result of our word count. You can see this double quote and has come 346 times. Double quote and comma has only occurred twice. Andrew with double quote has come twice. Double quote Andrew and exclamation has come once. Okay, Rohit wants to clean the data and remove dots and exclamation. All right. So here is a good point from Kamal. His point is, can we use reduce? Yes. So his question is, can we have our reduce like this? Yes. That's what I'm about to explain. Brilliant. All right. So what you're trying to convert is convert the counts, separate it by tab rather than separate it by space, right? And so that you can again feed it as the mapper. All right. Good. Yes, we can definitely do that. All right. So should we start now with the next part? Let's clean the data. Let's clean the data and try to run it. So what are we going to do is first substitute non-alphanumeric characters. This means non-alphanumeric characters. You see, this inside square bracket means not A to Z and capital A to Z and 0 to 9, and then replace it with nothing, meaning delete it. Okay, and then you say tr this. Let's try to check whether this program is correct or not. And all right, are you able to hear me? Because there was a power fluctuation. So Alright, I'm sorry. There was a power fluctuation. Looks like broadband also turns off on the power, even though I have all the backups. Sorry for this. Alright, so before the voice got interrupted, this is what I was trying to explain. So earlier we had only this as reducer. Now let's pipe this output and clean it a little bit more, remove non-alphabetic character, convert it into lowercase, and then send it as the key value to the mapper. Alright, let's try to run it. Alright, so let's try to edit my cmd.sh, or let's just try to run it just like that. Okay, alright, so here we go. If we had echo this exclamation is dot and then at the rate and then hash and then we send it. So now you can see that it has cleaned the data. It has removed all the letters which are non-alphanumeric. Also, let's also test if we put some of these in caps. You can see that it has cleaned our data. The first command is usual, replacing space with tabs. Alright, replacing space with tabs. Okay. Second is to replace non-alphanumeric with nothing, meaning deleting it. And then translating capitals to lowercase. The tr command translates. You can run each of these individual commands with echo and you will find what exactly each one is doing. Alright, now let's try to put, now we cannot provide this here. We cannot provide pipe here. Okay, we'll have to create a separate file containing this and then run it. Okay, so nano mycmd.sh. Alright, also please note that we cannot run a program just like this. Okay, if we try to run it, it'll say permission denied. You will have to say chmod plus x. So this is our first program which we want to test it out, as MapReduce. So let's see if it is running or not. Okay, yeah, it's running fine. So this mycmd.sh is cleaning up the data and converting a line into one word per line. Okay, text into one word per line. That's all it's doing. Alright, so if we have to execute it, there are two more things which we are doing here. One, this. One is this part. Alright. You can see this. There are two things which we are doing here. Extra. Alright. So input folder is same. Output folder has to be different, of course. My mapper is different this time. Okay. Now here we are providing the name of the command instead of instead of in, instead of the SED or anything else. Okay, so we can run this as, all right. Now here we can put slash slash and slash and slash. All right, slash we are putting so that we don't have to put everything in a single line. Now let's see what happens. Does it give an error? It says that input path does not exist. That's correct. So what do? We will change this to, we'll change this to slash data slash mr. All right, you can see the job here. What's going on with the job? What was the job ID? The job ID, where is the job ID? It will give you the job ID 0057. It's running, I think. Succeeded running. No, not running. Succeeded. Where's the 571? Did I make some mistake in noting it down? Oh, I'm logged in into somebody else's account. That's why I'm not able to see. Alright, here is the command that I'm running right now. Alright, so you can see that now we are in correct login. So now we can see that what happened to the job. Alright, this is a better way of observing, because when you are running in a cluster, you don't generally do things over the console. You generally look at, you run it, keep running it, or keep scheduling it, and then run it from time to time. So it shows you std error, it shows you the complete log as in what's going on. Alright, so you can have a look at it there. So minus file, there is something which we did not talk about here. One is that this command called mycmd.sh does not exist on all the machines. There are 3-4 machines in our cluster, and this mycmd.sh only exists on this machine, which means it has to be installed or it has to be shipped to all the nodes. Okay. Now, how do we do that? As in, if we have to run it over the cluster, then this command has to exist on all the nodes. This mechanism called distributed cache is something which Hadoop uses. Hadoop uses something called distributed cache to ship a file from one machine to all the machines. So this mycmd.sh has to be copied to all the nodes, and then it will be executed. So whatever program you have, whether it's a legacy code or any program, if you want to run it as mapper or reducer, you can ship it there. If there are multiple files, let's say file 1 for this mycmd.sh is using my library.sh, another command, or it's using xyz.jar. So you can ship it all of these together and send it to all the nodes. Okay. Now the other aspect is you can change number of reducers by using this particular argument. You can say change number of reduced task by saying -d mapred.reduce.task equals to 2. So now there will be two files in the output folder. Let's have a look. How many files are there in the output folder? So what was the output folder? Anyone? It is asgiri, word count and output. Asgiri and word count. What? Asgiri yeah, here. You can see there are two parts now. Somebody was asking that will there be two files in the output? Yes. Sounds good to you? All right. All right. So that was how we executed map and reduce using streaming job. Okay. So any questions at this point before we move forward? I'm assuming there are no questions because now Murkesh's question is the content of two output files the same? No. The output is not same. I'll show you why. Have a look at this. Let me open another one with these two files. So this one contains part 001. This one contains part 000. Now you can have a look. I'll just change it quickly. So this is the value and this is the count. Okay, this is the word and this is the count. So 005 went to the first reducer while empty went to the second reducer. Second reducer got 00 while first one got 01. Okay, so it's trying to distribute it uniformly. And how and on what basis which key goes to which reducer is decided by something called partitioner, and we are going to discuss partitioner in detail. All right. Now moving ahead. All right. So here are a few notes. All right. There is a okay. So Srinivasan question is, what is the command to execute mapper and reducer in Java? It's the same command. Just that instead of using Hadoop streaming.jar, you will be using your own Hadoop, your own own streaming. Okay, your own jar here. It'll be your whatever jar you create, that is what is going to be there. All right. So here are few notes which we learned from the discussion. It's okay to have a node reducer. If you had, you can basically have no minus reducer argument in the previous command. All right. In those cases, when you don't have a reducer, it is the mapper. It's the mapper who will decide how many files are created in the output. The way right now there are two files because there are two reducers. If there are no reducers and we say that we don't want any reduced task, then whatever is the output of the mapper will go directly to HDFS without passing through any reducer phase. All right. So maps will decide the number of output files. Also, the the number of mappers is decided by how many input splits are those. Input splits are equivalent to HDFS blocks, just that the boundaries are fixed and blocks are raw data and splits are kind of a data which you require for processing in the form of records. Now, it's a function of number of input splits. How many splits are there, based on that maps are decided automatically. Right now, since we are processing only a file of 6 MB, it's not doing much. Okay. But if you really want to change the number of maps, you can change it by setting number of maps. All right. Also, there's a common question that how many number of reducers do we want? Okay, how many number of reducers do we want? Whether to use two reducers or three reducers. So there is a general thumb rule which gives you a general guidelines between, it gives a range between this reducer to this reducer. So first you compute total number of tasks that can be executed on your cluster. If you have one CPU, generally you can execute by default the configuration says that you can execute two tasks at a time on a Hadoop node. Okay, so if you have if so you basically sum up total number of tasks in your cluster, and then total number of reducers that you would like to execute should be somewhere between 0.95 to 1.75 times the tasks. Okay, so it's an arbitrary number. It's not something people have done. I mean, they have done a fair amount of work to figure this range. Okay, but still this range is going to be bigger. Let's say you have 5 nodes and each node is having two tasks ability, as in each node has been configured to execute two parallel tasks at a time. So there are 5 into 2 because we have 5 machines and 2 tasks. Therefore total number of tasks that can be executed on our machines is 5 into 2, which is 10. Now as per this thumb rule, it says we can have number of reduces between 9.5 to 17.5. Okay, which means 9 to 17. All right, now this range itself is a huge range. Now imagine having 50 machines with 2 tasks each. Okay, imagine having 50 machines with two tasks each, meaning 100 total number of ability of your total amount of ability of your cluster is 100 tasks at a time, right? So 100 tasks means somewhere between 95 to 175. Okay, so it's a big range, it's a huge range, it's a 95 range. It varies by 2x. So to decide between to decide which what number should be good for reduce, you need to see, you need to observe whether your reducer is faster or slower. Is it taking more time? Is the time that has been consumed, is the time that has been consumed in the time that has been consumed in transfer of the data is more, or time taken by actual execution is more? You can see this time using here. Okay, so if you have lot of time going in the reduce occupied slot, okay, if this is higher, and the time taken by the network, where is the network transfer? All right, yeah. So basically you observe that how much time is spent by all reduced tasks. Okay, how much time is spent by all reduced tasks. If this is considerably higher, okay, that means your reducers are really busy. Therefore you need to increase number of reducers. All right, so you can do a kind of a search in that range. All right, now here are some problems which I would like to discuss now. Okay, is everybody ready? Is everybody ready for discussions of the problem? All right, so do you want to discuss these problems, or should I leave those as assignment? All right, here's a question for all of you. If you have to count the frequencies of letters, do you use MapReduce? Will you need MapReduce, or one single machines will be enough? Yes? Good, good, good. Peter says that it depends on the size of the file. Okay. Carlos says maybe use Python. We may need MapReduce. That's Rohit. Frequency of letters in the above example. No, any. So, Murkesh, here we are talking about you given a huge file. You given a huge file, and you have to count the compute the you have to count the frequencies of the letters. Harita says that MapReduce is needed for the large size. Good, good, great answers. This is what I have been looking for. All right. So this is very important to understand that it is the data size that governs most of the things. Okay. It's not your design patterns per se. Design patterns or any other programming language, this or that, is generally a function of what are we trying to achieve and how big the data we have. Earlier, we never thought of the strategies because we always thought our database can get everything done for us. Therefore, now whenever we encounter a big data problem, you generally have to analyze based on the amount, volume and velocity of the data. If somebody says that they want to do stream processing and you ask them what does it mean, what is the throughput are they looking for, what is the input data speed that is coming in, if it is below, it is in minutes, then there is no point in going for a higher end framework. So similarly, you do these things. Any of the design decision you take upon what is the input as well as what is the desired output. All right, good. Now coming back to the frequencies of ladder. So how much do you think would be the size of the file at that point we should move to MapReduce instead of getting it locally done? So on what size should we go for MapReduce for 1 GB? Okay, so let me ask you this way. Running up to which up, up to which size is okay on one node? 4 GB, 10 GB, 100 GB. Yes? Pankaj says more than per terabyte require multiple nodes. It depends on the hard disk size. Okay, okay. Peter, Anand, Harita, Murukesh. Peter says 10 gigabyte. Yes, that's right. So up to 10 gigabyte, it's okay for to run it on a single node. Why? Because how much does 10 gigabyte take? 10 gigabyte is equal to 500 seconds. Not It's equal to 50 seconds. Okay, because it takes around 5 seconds to read the gigabyte data from the disk. Therefore, reading reading 10 gigabyte will take around 50 seconds from the disk, and therefore computing on 50 seconds is really okay if you do that. So the if you do it parallelly, read one. So parallelly you keep on reading from the disk, and parallelly you keep on computing the number of characters, unique characters. So it should be very straightforward, and it's only the disk which is the bottleneck, the disk I/O, and therefore the time which is going to it's going to take in the best case scenario is 50 seconds. Okay, so 50 seconds is normal, because if you try to use MapReduce for for this kind of job, it's going to take more time. Okay, and therefore the MapReduce may not be great up to 10 GB in the input size. Yes. All right. So the reason is, although we can always say it all depends, but the reason is it takes around 50 seconds. And if you run a typical MapReduce job, it might take it might take 50 seconds easily in a normal batch process. Okay? In a normal batch process, it might take around 50 seconds, just like that. All right. So the without MR approach, it's pretty straightforward. You take an integer array of 26 size, scan the text character by character, increase A0 for A and increase A25 for Z, and others in between. Okay, so this approach is clear. So although memory RAM is not a constraint in such a problem, it is the network or the disk IO which is the bottleneck, and therefore you might need a MapReduce. Alright, who can help me in suggesting what should be map and what should be reduce in case we want to go for map reduce in frequencies of letters? We have got 100 gigabyte of data, 100 gigabyte of plain text, and we want to compute the frequencies of letters. Okay? So what do we need to do? Anybody? Peter suggests that map instances for each letter with A as 1, A as the value, A as the key and 1 as the value. Okay. All right. Harita also says key is going to be letter and the value is integer. Good. Good. Murkesh says key will be the alphabet and value will be the count. Good. Good. Each word as the key value. Each letter would be a key value, Pankaj. I think that's what you meant to say. Peter says that reduce based on the sum of the value at the end. Yes. Alright, can anybody optimize this? Everybody is suggesting me that put the key as alphabet and value as 1 for each of the line. Now you can imagine that at the end of every line you will have maybe hundreds of characters. Okay, can you little bit optimize it? Hundreds of key values. So, alright. Okay, good Kamal, good Anand, good Murukesh. Alright. Can anybody optimize it a bit? So what we are doing is here in the first approach, we are doing something like this. So what exactly are we doing? Let me increase the size. Let's say this is a cow. Okay, and it lives in jungle. Or let me just put it, who lives in jungle. Alright, let's say this is the one. So what all of you are suggesting, take each character and take each character and put it in a single line, and this is what you are suggesting, right? Okay, and then do the sorting. The Hadoop will do the sorting, and then you will say the unique minus C. Okay, so A has occurred once, and you can see I has occurred 4 times, and so on. E has occurred twice. All right. Do you suggest any other approach? Because the main challenge which I foresee is the total number of keys will be equal to the total number of alphabets in this. While while if you look at it closely, there are only 26 alphabet. Why do we need so many keys? Can we reduce it a little bit? All right. So one way is that for each line we compute the frequencies. Okay. We compute the frequencies of each line, and rather than putting t as one, I as one, as a result of it, we will put I as 4. Okay. Since in case of map we will get the full line as input, so we can compute the frequencies of that particular line and then put it in the output. All right. Other than this, we can also tweak MapReduce a little bit, that we will consider in future. There are many ways to optimize it. All right. There are many ways to optimize it. Yes, that's correct, Rohit. Here, Mapper is doing the job, reducer job correctly. Mukesh is saying how do we get familiar with these kind of approaches? You basically have to try more things. You have to try to do it by yourself and then think about how you can optimize. Okay? All right. So what we are doing here is, in case of, okay, so in our mapper process, in the mapper phase, what we are doing is, for each line we are computing number of A's, B's and C's, and then reducer is summing up all these values. Okay. So instead of key one, key two, I mean A1, B1, C1, we are first computing the frequency in each line, and then printing the overall aggregate, rather than letting Hadoop do the whole job. So we are partly doing the reducer job. That's correct, Rohit. All right. Do you think this approach is good? Anand says we can do this on page wise as well. Good. Instead of reading line wise, if we could configure Hadoop that give us one page at a time, then it could have been a little faster for us. Correct? Now, there are many more approaches. There is one thing called combiner. Okay, so before taking the data from mapper 1 to the reducer, this combiner will shrink, or combiner will reduce the values on mapper node itself. So a combiner is per node reducer. We will see that at a later point of time when we discuss the partitioning. All right. Now the next question to all of you. This is little tricky question. All right. This is little tricky question. Question to all of you is, you are given a huge text and you have to find anagram. You have to find anagram. An anagram is basically different arrangement of the same word. For example, CAT and ACT are two different arrangement of three letters A and C and T. All right. Now, now, how would you write your MapReduce program such that all the anagrams should come together? If you have to bring all the anagrams together, what is it that we are going to do? Anagram is not reverse of the word. Anagram is just rearrangement of the letters. Anybody? Yes? Yes. What will be the key and what will be the value? What is that word that is going to be the key? Murukesh? All right. Our objective is to provide key values instead of because we size of this file is too big that we cannot afford to search by ourselves. Okay, we cannot afford to search by ourselves. Therefore, we are letting Hadoop do the job, and all we need to do is devise the key such that all of these anagrams come together. We have to devise a key which is common to all of the anagrams. And what is it that is common to all of the anagrams? That word which is common to all of the anagrams of a word. What is? How would you form such a word? Based on given a word, how would you find? How would you bring all the anagrams together? All right. Pankaj says that split each word and then each letter of the word to other, and then find each letter of each word to the other. Peter says key is the actual word, value is the unique sorting of the word, or is it the other way? Murukesh says we need to compare word against a dictionary kind of thing. Harita says hash as the key, okay, and the word. But what is the hash? Hash is just a number which is computed by uh, summing up ASCII code and dividing it by some value. Is it guaranteed to have this kind of output? Will hash of cat, tag, and ACT will be the same? Okay. Peter says then, all right. Let me just read out the full point. Then it will only then it will make sense. All right. Key is the actual word, and value is each unique sorting of the word. Then it is matched up to key to value at the end to find potential anagrams. How about key being the unique sorting of the word? Will that be same for all? Okay, Kamal says that should we keep the key as this, meaning all the rearrangements of the letter, Now, for each cat, act, and tag, this is what you want to do. Yes, good, good. This approach is also clever. So I've got two, three approaches. Brilliant. So here is Anand's approach. So A to Z word with all alphabet. I'm assuming that you are talking about a big array in which each uh, value, big array of 26 words, in which each value is marked with which character is present in this particular word. Or am I just thinking that way? Rohit says that map key can be word and then compare each word if exists by rearranging letter of the word. We cannot compare because you can imagine that if there are a billion words, will you compare each one against each one? That will be an impossible work. Yeah? Is my voice breaking to all? Alright? So, yes. Alright, brilliant. Here is one of the answers. Peter says that key is the sorted characters of the word and value is the word that is found originally. Do you think it's correct approach? Anybody? Yes? Do you think this approach is correct? Anand, Rohit, Kamal, Murukesh, Harita, Dilshad. Is this approach correct, the one in the last line? Yes. So this approach is correct actually. Great. Thank you, Shah. All right. So, yes, here is the approach. So here, this is what I have drawn in the diagrams. So the mapper, let's think about the cat act in tic-tac-toe. Mapper is giving out, somebody has raised a hand. Yes, Murukesh, you have a question? You raised a hand? All right. So what are we doing here? As part of mapper, what could be that key that will be the same for all the anagrams? No matter what is the anagram, if you generate that key, it should be same for all. What could be that key? The key is to understand the meaning of an anagram. Anagram is rearrangement of the letters, meaning it's the same set of letters, it's just the arrangement is different for different in all anagrams. It's just the arrangement. So if we dearrange them, if we make them a same arrangement in everywhere, that means it will result in the same thing. So for example, if we sort the letters, that means THE, if we sort the letters such as they become alphabetic. So E comes before H comes before T. Similarly, for cat, we rearrange the letters and it becomes A, C, and T. Okay, so for the, our mapper is converting it into key value pairs where key is the sorted character sets. Okay, so the key is ETH and the value is THE, the actual word, original word. In case of cat, the key is ACT. In case of cat, key is ACT. In case of in case of act, the key is ACT, and in case of the key is in. TIC, I comes after C and T comes after I. So it will be CIT. This is alphabetic, the way it appears in the dictionary. The characters are alphabet have been sorted. Characters have been rearranged such that they have an alphabetic order to follow. The idea is it's not necessary to have this alphabetic ordering. It could be reverse also. It could be reverse also. Basically, we need to find a key that is common for all the words, so that we when, so that Hadoop automatically brings all these anagrams together for you. And why would Hadoop bring it? Because Hadoop works on the key and bring all the values of the key together. Therefore, all you have to do is somehow figure out a way to produce the same key for all the values which you want to bring together. And that's what we are trying to do. So TOE, EOT. Now you can see that Hadoop, this line is what is meant by Hadoop. So Hadoop will convert it into ACT, and then it'll bring all the anagrams together. And reducer does not do anything. Reducer simply finds unique words from these anagrams and print it. That's all. Is the anagram problem clear to all of you? Is it clear to all of you? All right. Any questions on anagram problem? This one? All right. Now here is a simpler problem. This probably all of us can help in this. Let's say there is a big file of DNAs of the people, DNAs and their names. And now you have to find all the people who have same DNA. You have to find all the people whose DNA is identical. So your input file is user ID space DNA. Second, user ID space DNA. In this format, if you have a big file containing people's DNA and their ID, name and the ID, name and the DNA, then all you have, the objective of the exercise is to bring all the people together whose DNA is identical. So for in this case, user 1 and user 4 both have the DNA ACGT, and user 3 and user 5 both have the DNA as ACG. So, so in this case, what would be your mapper and what would be your reducer? What is it that you will write the logic in mapper and reducer? What will be the key and what will be the value in case of mapper, and what will your reducer do? Anand says key is DNA. Murkesh says key will be DNA and value will be the user list. Brilliant. Peter also says key DNA value user. All right. Brilliant. Anand also says key is DNA and value will be the users. Brilliant. Pankaj says mapper will read each line, put the DNA pattern as key and the user ID as value. Brilliant. And the reducer does nothing. Good. Good. So Harita says that DNA is key and user is value. All right. All right. Rohit says reducer will print values after sort and merge. Brilliant. Srini says user as the key and DNA as the value. No, no, Srini. The because our values we want to aggregate people having DNA same, right? Therefore, DNA will be the key. Okay, we want to group our data by DNA. Therefore, DNA will be the key. Carlos says mapper keys DNA and reduces for distinct. Brilliant. Reducer is for distinct. That's correct. Carlos, good, good. Dilsa say key a DNA and value user ID. No work, not much work for reducer unless um, okay. All right. Pankaj says that no work for reducer. Hadoop framework will sort and merge the output of the reducer. The only work you may want to do it in users is maybe you would like to remove the duplicate users in case there are, as Carlos was suggesting. Good. Brilliant. Brilliant. Excellent. So yes. So the key will be the DNA and the value will be the user. Now there is another slight twist in the story. There's a slight twist in the story. The twist is one scientist came along and said, it's not only the DNA, it's also if the DNA of one person is just mirror image of another person's DNA. If the DNA of user 1 and user 2 is a mirror image of each other, you can see DNA of user 1 is ACGT and DNA of user 2 is TGCA, which is the reverse of ACGT. So this scientist came along and said that you know what, all the people who have identical DNA or mirror image of DNA, they all belong to the same family. Let's try to bring them together. Let's try to bring such users together. Just there is a minor problem. The problem is the data is too huge. These are billions of entries in this file. Now, question is, how would you use MapReduce framework to bring such users together whose DNA either are identical or is mirror image? Anybody? This is tricky. This is tricky. And yes. So here, user 1, user 2, and user 4, they have the same DNA or the mirror image of each other. User 1 and user 4 have identical, while user 2 has just the mirror image. User 3 and user 5 have identical DNA, while user 6 is not with anyone. Can somebody suggest a way to form key for each row such that the key for user 1, user 2, user 4, ACGT, TGCA, and ACGT, the key remains identical. Can we form the key for all of these which will be same? When we were looking for anagram, it was simple to bring all the characters. We just keep the distinct characters. Now here we just we just need to see what should we prepare the key such that mirror image and the DNA, they all come together. Murugesh says for the map, the key could be opposite. If you do the key opposite, let's say ACGT becomes TGCA and this becomes ACGT. Okay. Again, when Hadoop looks at it, Hi, I again lost the sound. Yeah. All right. I think we can discuss these problems in next time. Let's just finish. Let me describe the problem statements and then it'll be easier for you. So there is one more problem which you need to solve. The problem is in this unusual democracy. Wow. I think Pankaj has got it right. And okay. All right. Let me just describe the next problem and then you solve the problem in the LMS and let me check it later. All right. All right. The next problem is in this unusual democracy, you have got people who vote for each other. But the difference is that instead of everybody being equal, the person who has more wealth or the person whose worth is higher, his vote matters more. In this unusual democracy, if a person is being voted by somebody really rich, gets more vote. So, to do the vote counting, you need people's bank account details as well. Therefore, there are two files here. First, who voted for who, and second, whose worth is how much. Now, you have to find out who won the election. Okay? For that, you have to do the vote count. So let's say there's list one and list one containing votee and voter. A voted for C, B voted for C voted for F, voted for B, and F voted for C. And you have second list which has person and their worth, meaning A has got a worth of 5, B has got a worth of 1, C has got a worth of 11, and D has got a worth of 12. Therefore, A, who is voted by nobody, gets 0 as vote count, while B, who was voted by A, B was voted by A, and A's worth is 5. Therefore, B's vote count is 5. C was voted by A and B, and therefore A and B is 5 plus 1, and therefore C's vote count is 6. F has been voted by C, whose worth is 11, and therefore F's vote count is 11. So who voted for who? Ba- Based on that, we are computing how much is the vote count by combining it with worth. So there are two more things I need to tell you, that this problem involves having multiple map reduce. You can have multiple chain of map reduce, having in the sense that first map reduce phase will put the output in HDFS and that will become the input to the second phase. So you might require multiple phases of MapReduce to solve this problem. Second hint is that if list 1 and list 2 are kept in the same folder, they will be concatenated for your MapReduce input. Okay, so try to solve this problem. If you have any doubt, just drop me an email and I will help you out. All right. So rest of the things which we'll discuss in the next time. Till then, please try to solve this subjective questions. Okay, it is mentioned in the session 2. We will rearrange these because we have introduced lot many topics, so we need to rearrange the LMS a bit. Okay, so this is the problem, you can see that. So you have to solve it and submit it. All right, that's pretty much for today. And sorry for getting disconnected again and again. Let me try to fix these problems. All right. So please solve these 5 problems and let me know in case you get stuck. All right. Have a good day and a great week ahead. Bye bye. All right. Thank you, Peter. Thank you, Srinivasan. Thank you, Harita. Bye bye. Have a great week ahead. Thank you, Kamal.